Welcome back to Physical Chemistry on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to my channel for future videos and notifications. In this video, we're going to be working an example problem for osmotic pressure. Now, the gist of this problem is we're going to be given an osmotic pressure, and then we're going to be asked to calculate the molar mass of the solute that's contributing to that osmotic pressure. And so we're going to begin with this formula right here where we have capital pi. This is the osmotic pressure. It's equal to the ideal gas constant times the absolute temperature times the number of moles of the solute, and then you divide by the total volume of the solution. Now, in this form of the equation, we don't have anything that indicates molecular weight explicitly. However, if you have a problem where you need to interconvert between osmotic pressure and molecular weight, there's a very important relationship that you need to remember, and that's the fact that moles is always equal to mass divided by molecular weight. Okay? So what it turns out we can do is take this n, the number of moles of the solute, and replace it with this quotient right here, the mass of the solute divided by the molecular weight of the solute. And so everything else remains the same. We still have RT over V, and then N has been replaced with little m, which is mass, over big M, which is molecular weight. And again, notice that these moles, or mass, or molecular weight, they're all with respect to the solute. So let's read the question and figure out how to solve this. Hemoglobin, which is actually shown down here, is a large molecule. It's a protein that carries oxygen in human blood. A water solution that contains 0.263 grams of hemoglobin in 10 milliliters of solution has an osmotic pressure of 7.51 torr at 25 degrees Celsius. What is the molar mass of hemoglobin? Now, to do this, we're basically going to rearrange this equation and solve for the molar mass, big M, of the solute. Now, bypassing all the algebra that we'd have to do here, essentially if we set pi, osmotic pressure, equal to RT times the mass of the solute divided by the molar mass of the solute divided by the volume, if we take that expression and we solve for the molar mass of the solute, we're going to get this expression right here, and you should practice doing that. The molecular weight of the solute, or molar mass of the solute, is equal to the ideal gas constant R times the temperature times the mass of the solute divided by the osmotic pressure divided by the volume. Okay? Now, we're given the osmotic pressure in units of torr, 7.51 torr, so what we're going to need to do is select a gas constant that is in terms of torr. So here's our expression for molar mass, or molecular weight of the solute. I'm going to use this form of the gas constant. Again, you can look these up, but the value is 62.364 liter torr per mole per Kelvin. The reason I choose this is because if my osmotic pressure is in torr units, these torr units right here will cancel, and I'll actually show you how these cancel specifically. So let's actually get a little red line right here, and we will cancel units as appropriate. Okay, so again, we have this as our gas constant. The temperature we need as an absolute temperature. Again, we have this gas constant that has Kelvin units. We need a Kelvin unit here. It's always safe to just go to Kelvin units. So 25 degrees Celsius, we would just add 273.15 to that, and we get 298.15 Kelvin. We're going to take that and multiply by the mass of the solute. So again, M of the solute. Well, we know we have 0.263 grams of hemoglobin, so 0.263 grams. We divide by the osmotic pressure, that's 7.51 torr. So that goes here as pi, and then the volume, we're given it as 10 milliliters, but because our gas constant has units of liters for the volume part, this needs to be in liters. And so to convert 10 milliliters into liters, we would just take that 10 and divide by 1,000. And that would give 0.01 liters. Now again, here's where we can start canceling units. So again, the liters here are going to cancel with the liters in the denominator. The pressure units, so torr down here for osmotic pressure, will cancel with the pressure units up here. The Kelvin units right here will cancel with the Kelvin units right here. And then you say, but wait a second, now we don't have anything that'll cancel. Well, that's the point, right? Because the units that are left are grams and then per mole. Well, grams per mole are the units of molecular weight. And so that's what we're left with. So we simply multiply all this out and divide by the denominator here, and we get a number that's approximately 6.51 times 10 to the fourth, and the units would be grams here per mole. And so this would be the approximated molecular weight or molar mass of the solute, which in this case is hemoglobin. So with this type of problem, if you know you're dealing with osmotic pressure in some way, it either asks you to calculate that or it gives it to you, and you also have molecular weight, then you'll need to use this substitution for the moles, which is the mass of that solute divided by the molecular weight or molar mass of that solute. So hopefully this made sense to you. Please make sure to like this video and subscribe to my channel for future videos and notifications. Thank you.